Right. And our next talk will be given jointly. I think this might be the first. No, Michelle and Jamie did a joint talk last year. The second joint talk given at PCC. It will be given by Sasha Cohen and Bryn Bailey, who are doing it from their own computers. From where you are you coming up?
If that's
Okay. Sure. Those of us in the first two rows will just turn around. Go ahead and shut off this video and I'm going to go ahead and hand you the microphone. Cool. So that you have.
Thank you so much. Hi, everybody. My name is Bryn Bailey. This is Sasha Cohen. We'll be talking about our planetary defense work over at UC Santa Barbara in our NASA Innovative Advanced Concepts Phase 2 study. Some of our collaborators are here in this room and online, so thank you for being here. And we'll kind of be swapping back and forth, so just be patient with us. Okay, so of course, as we all know here, space debris entering Earth's atmosphere is not uncommon and usually consists of small bodies or fragments of bodies that are generally not considered threats. But on occasion, we may be visited by larger objects that do have the capacity to enact damage. And traditionally, planetary defense efforts have been focused on deflection through kinetic impact. NASA's DART mission from a few years ago showed us for the first time that we can use deflection to push something out of Earth's path if necessary. But a deflection mission hinges on a few key parameters. First, we have to see the asteroid coming, and this must give us enough time to design and launch a mission to deflect it relatively far ahead of its impact time, which is on the scale of years, if not decades. And while most NEOs are small and non-threatening, there's always some possibility that something larger could come by or something that we don't see far enough ahead of time. Some historical examples, of course, include the Chelyabinsk airburst of 2013 and the Tunguska airburst of 1908, which demonstrated our need for both detection and mitigation efforts. So in any case, current planetary defense strategies are not well equipped to combat a wide range of threat scenarios, particularly in the short warning regime where there's little to no time before impact. To achieve an extensive planetary defense system, it's imperative that we're prepared for a wide variety of threat scenarios that considers a large range of threat sizes and warning times to prepare us for anything. So that begs the question, can we append existing planetary defense technologies with a new approach that can provide reasonable mitigation of a wide variety of threats, including those in the short warning regime? And now I'll pass it over to Sasha Cohen.
And our hopeful answer is yes. Our method uses hypervelocity penetrators to couple their kinetic energy into the target via shockwaves and material vaporization. I'll show a quick example of that. This is a 100 kilogram tungsten impactor impacting a granite target at 10 kilometers per second. You can see how over the course of a few hundreds of microseconds, the entire object is vaporized and you get this long channel of vaporized material, and all of the kinetic energy is converted into the temperature of that vaporized material and shockwaves which evolve through the object. Now, the next step is to allow those shockwaves to progress through the object, and that damages the material and crushes out the porosity, which again reduces the overall cohesion of the object. Ultimately, then, the asteroid is disrupted into a cloud of fragments, which disperse at velocities that are much greater than the original escape speed of the object. And so you can be fairly confident that none of these fragments will come together again and recombine into an object during the course of its trajectory from the mitigation time to when it would have impacted the Earth. Now, for most impactors, this is where the story ends. The fragments spread out into a diameter that's much larger than the radius of the Earth, much larger than the diameter of the Earth, and then the threat is effectively mitigated. However, there are some cases where you would like to mitigate a terminal threat, in which case we have studied the ground effects of allowing a distribution of fragments to enter the atmosphere and have found that it does a fairly good job of dispersing the total impact energy. And so we are fairly confident presenting a method of planetary defense that can operate in both of these long warning times and short warning scales as well. So here's a brief description of our simulation setup. We use the Livermore code AL3D. It's a Hydra code, and we use the NASA Ames high-end computing capability to run our simulations. Our baseline passive penetrator is a 10-to-1 aspect ratio tungsten cylinder with a yield strength of 750 megapascals. And our target, as you can see on the left, is a heterogeneous collection of boulders, which are set inside of a weak binder material. The material uses we use the Livermore equation of state tables. These are discrete equation of state tables to describe the materials. And the asteroid material has a density of roughly 2.6 grams per cubic centimeter. We also introduce a porous crush model based on investigations of impacts into porous materials. The boulders themselves have distributions of yield strengths within them, which are defined by the Weibel distributions shown at the right. The colors of the boulders on the left correspond to each of the Weibel distributions on the right. So you can see how we have some boulders which are fairly weak, 1 to 5 megapascals, and some that are extremely strong, 250 to 500 megapascals. And this is a fairly conservative approach for modeling these materials because we don't actually expect these materials to extend into that high strength range, but we like to say that we can mitigate these sort of diabolical threats if they exist. So here's an example of a simulation of a single 100 kilogram impactor impacting a 50-meter rubble pile. I'll go ahead and let this animation play while I talk about it. And ultimately, what it shows is catastrophic disruption. The mass is so low that this is indicative of what we like to call a single launcher solution for planetary defense, where you could, for example, maximize the payload capacity of a SpaceX Falcon 9, which happens to be 2.5 metric tons, and be fairly confident that you could mitigate threats within the 20 to 150 meter range, as we're showing here with a particularly small impactor. And then we can do some interesting statistical analysis of the fragments after the fact, which is shown on the left. We have histograms of the fragment masses shown in gray, histograms of the diameters in blue, and histogram of the speed in red. You can see how the original escape speed, shown as the vertical dashed line this is the original gravitational escape speed of the object, is only like 2 centimeters per second. And the histogram of the fragment velocities shows that the average fragment velocity is roughly 3 orders of magnitude higher than that escape speed. So you've done a fairly good job of disrupting this object. Another interesting parameter to note is shown in blue. This is the specific impact energy. This is defined as the amount of kinetic energy from the impactor per unit mass in the target. Studies of sort of sphere-on-sphere or asteroid-on-asteroid type impacts have shown that a specific impact energy of roughly 100 joules per kilogram is sufficient for catastrophic disruption. And so you can see how we should expect at 236-ish roughly joules per kilogram that we should see catastrophic disruption. And that is indeed what we see. Here's another example showing where we quintuple the mass. We have a 500 kilogram penetrator instead, and you can see how the specific impact energy has also increased as well. Moving on to a discussion of the internal dynamics of what goes on inside of a penetrator as it's impacting an object at hypervelocity. We've done a number of 2D axisymmetric simulations at fairly high spatial mesh resolution to discover or to learn what happens inside of the penetrators. This is the same tungsten material model for the 10-to-1 aspect ratio penetrator and the same granite target, except this time instead of a boulder distribution, we just show a single heterogeneous target. We show density on the top, pressure in the middle, and temperature on the bottom. This is the same simulation that I just showed before. And this is at 10 kilometers per second. And notably, if I switch over to the next slide, you'll see the same thing at 20 kilometers per second, which is a much more violent impact. And there are some sort of qualitative observations to note, which I'll discuss further later, but specifically note how there's a sort of frictional interaction with the vaporized material adjacent to the side of the penetrator, which is producing an in the penetrator, which you wouldn't normally expect to see because you're at a hypervelocity. You're impacting at much higher than the sound speed in the material, but because you're surrounding the sides of the penetrator with vaporized material, you actually do get a frictional interaction. You get acoustical signals inside of the penetrator. Now, one thing that would be interesting is to study how one might supplement a passive mitigation with nuclear explosive devices to potentially mitigate threats that are coming in at slow speeds, where the kinetic energy of a passive penetrator is not enough to disrupt the object, or where the object is particularly large and you just don't have enough kinetic energy from your impactor, even if you're arriving at, say, 20 kilometers per second. So these are 2D axisymmetric simulations similar to the ones I showed before, except there's a suspended mass in the back of each penetrator. And this is meant to simulate some sort of a fragile device, which is hopefully isolated from the G-loading that hypervelocity penetrator might see. These two simulations on the left is at 5 kilometers per second, and on the right is at 10 kilometers per second. And then at the center of each suspended mass, I've placed a tracer particle, and then the plots on the top show the G loading in the X direction for that suspended mass. Now, what we see is a sort of zone of survivability between 5 and 10 kilometers per second, where above 10 kilometers per second, that frictional interaction with the adjacent vaporized material produces an acoustical signature that's high enough to actually sort of deform that back part of the penetrator and potentially destroy your fragile device before it makes it far enough below the surface. And then the other, if you're below 5 kilometers per second, you're slower than the sound speed in the material. And so you subject the back of your penetrator to the high magnitude shocks that would be generated from the impact of the front. However, this comfortable zone between 5 and 10 avoids both phenomena, and it's indicative of this potentially comfortable region where you could mitigate an asteroid with a nuclear explosive device. We simulate these impacts with a sort of energy pill. This is similar to the method described in Schroeder 74. In this method, radiation transport isn't explicitly calculated. Rather, we just inject energy into a sphere of material, which sort of pre-vaporizes the material. It's an analog to how the radiative output of the device would be absorbed rapidly locally to the site. On the top is an example of one of those for a 10 kiloton detonation, and then the simulations I'm showing here at the bottom are for a 1 kiloton detonation, which, if you look at the description of the radius for this energy pill, 2 times the yield in kilotons to the 1/3, at 1 kiloton, that leaves a really nice 2-meter radius detonation, which I'm showing in high resolution on the left. And then what you saw earlier is the longer timescale evolution of that situation where the asteroid is allowed to completely disintegrate into fragments. And the color scale, in this case on the right, shows the speed of the fragments. Moving on to ongoing work, we're interested in other ways that you might deliver a penetrator even deeper below the surface, more deeper than one might achieve with just a single penetrator. And there are 2 potential ways one might do that. One is with close sequential penetrators, as I'm showing here, where the penetrators closely follow each other. And you can greatly increase the penetration depth in this mode. However, you are basically ensuring that the follower penetrators have to survive traversing the vaporized material behind the leading penetrators, and that's still an open question as to whether that's possible. The other method is sequential penetrators with significant spacing, where you allow the entrance cavity of the leading penetrator to evolve in time, and hopefully the density and pressure on the inside is decreasing enough to where the survivability for the following penetrators increases. And then finally, in the future, we're hoping to move towards actual asteroid shape models as our targets rather than just simple spherical targets. And hopefully this will allow us to investigate more complex mitigation scenarios, such as contact binaries, where you have 2 lobes of the object which might be weakly acoustically coupled. So if you were to just impact one of the lobes, you wouldn't necessarily expect the shock to strongly couple into the other lobe. And so you have to introduce more redundancy, perhaps arrays of penetrators or explosive devices. And with that, I'll pass it on to my colleague Bryn to talk about ground effects.
Okay, so now we're going to move away from the impact stage and talk about what happens afterwards. So now we know that pi represents a versatile, multimodal approach that could be used in a wide variety of scenarios, whether the warning time is on a scale of days or years, or for threats like Chelyabinsk or like Apophis. So in longer warning scenarios, where an impact is months or years away, the fragments can miss Earth entirely, completely removing the threat. And depending on an asteroid's size and speed, a short warning mitigation scenario could be feasible. In these short timescale intercept scenarios, which, as Sasha referred to as terminal scenarios, the fragment cloud would enter Earth's atmosphere, where it would disperse the energy of the original asteroid through spatially and temporally decorrelated ground effects. And of course, PI's preferred mode of operation is in the extended intercept regime, where we would intercept an asteroid far ahead of its impact. It's, of course, preferable for any method of planetary defense to be used as far ahead of time as possible to keep any of the aftermath away from Earth. But in any case, our findings do suggest that Pi is uniquely capable of operating in a terminal mode in certain scenarios where the factors are favorable. So, to talk about the ground effects in the terminal mode during atmospheric entry of the fragments, the pressure exerted by the atmosphere eventually exceeds the fragment's material strength, causing a cascading breakup event. And as pressure and heat increase, the fragment ablates and the material fails, causing the fragment to burst. Collectively, these bursts produce optical flashes and decorrelated shockwaves on the ground. These optical and acoustic ground effects spatially and temporally distribute the energy of the original asteroid, which in reasonable mitigation scenarios that are appropriate for the threat result in little to no damage. Now, we design our terminal scenarios to keep the ground effects below reasonable thresholds to make sure that no unwanted damage occurs. So to prevent that high level damage from occurring, we aim to keep the acoustic effects we aim to keep all shockwave overpressures below 3 kilopascals, which is the point at which residential windows may begin to break. And for the optical effects, we aim to keep the cumulative optical energy below about 200 kilojoules per square meter, above which organic materials like paper or grass may begin to catch fire. So here we simulate the acoustic ground effects in a terminal scenario. Both boxes are looking at an asteroid that's 50 meters in diameter with an exo-atmospheric velocity of 20 kilometers per second and an average density of 2.6 grams per cubic centimeter. In the left box, we disrupt the body into 1,000 fragments 1 day before Earth impact. And in the right box, we simulate an equivalent unmitigated asteroid airburst. The upper movie plots display the real-time pressure, and the cumulative distribution functions on the bottom show the frequency of occurrence of various pressure values. And note that in the fragmented case, the simulation includes constructive interference from overlapping shock waves. In the fragmented scenario, we achieve an average pressure of about 600 pascals and a rarely occurring maximum pressure of about 2 kilopascals. So at no point during the simulation do we reach that 3 kilopascal limit, even accounting for the interaction between various shock waves. Whereas the unfragmented case has an average pressure of about 5 kilopascals and a maximum of 20. So these results suggest that pi can be effective in terminal mitigation of smaller objects, and combined with detection efforts, could potentially prevent events like Chelyabinsk or Tunguska happening in the future. As for the optical effects, here we're looking again at the same 50-meter asteroid cases with the fragmented on the left and unfragmented on the right. And again, we see that disruption really works to decrease the optical energy flux to manageable levels. In unmitigated cases like Chelyabinsk, of course, the optical output caused retinal and skin burns for those who are outdoors and unprotected from the flash. Mitigation via fragmentation in short warning scenarios could help to decrease similar potential damage. On the other end of the spectrum, simulations also suggest that pi is capable of mitigating much larger asteroids given longer intercept times. So here we're looking at a 500-meter diameter asteroid broken into 100,000 fragments with an intercept 60 days before ground impact. Of course, this is a much larger asteroid, so it wouldn't airburst. It would, in fact, impact the ground, which would be a much worse day for us. And while this intercept is certainly longer than the last, where with the 50-meter scenarios, I was showing a 1-day intercept, and this is now 60 days, this is still remarkably short. And of course, we wouldn't do this in any case that it wouldn't be absolutely necessary. We don't want to blow up an asteroid and have all of those pieces come hit us if we can help it, but it'd be a better day to have a little fireworks show rather than a giant crater in the ground, as the rest of you in here know far more about than I do. And in any case, designing and launching a deflection mission takes place on the scale of years, whereas this is just on the scale of months. So here, in addition to the real-time pressure in the upper left, we also plot the maximum pressure in the upper right, where every pixel in the simulation holds onto the highest pressure value it experiences throughout the current length of the simulation. And of course, on the bottom, we just have some statistical plots to keep track of things as they move along. And again, we see the cumulative distribution function in the bottom right, which shows us that the pressures experienced throughout this scenario are reasonable. We do hit that maximum pressure of just around that 3 kilopascal limit. So of course, we want to avoid that whenever possible. But this is an extreme scenario. There's really not a realistic scenario in which case we would have to do such a thing with such a large asteroid. We would, of course, in 99.999% of scenarios, see this far ahead of time and not have to resort to a short-term mitigation scenario. But we just, simulate these to show that it is in fact possible. And again, here is that optical simulation for the same 500-meter diameter case. So now in the upper left, we have the optical power flux distribution, and the upper right shows the optical energy flux. And again, the CDF in the bottom right shows us that we're keeping things lower than that energy threshold of 200 kilojoules or 200 kilojoules per square meter. So nothing here is going to catch fire. Feasible, really works to mitigate that energy dispersal. So kind of moving on, in the event of a nuclear mitigation scenario, there would be neutron irradiation of the asteroid material with subsequent induced radioactivity, in addition to the induced and residual radioactivity of the NAD or nuclear explosive device after detonation. So to simulate this, we use Lawrence Livermore's Livermore Weapons Activation Code, or LWAC, which is a neutron transport code that estimates the various components of the radiation source term given a specific set of inputs by the user. LWAC is a point model and therefore does not require a description of either the physical dimensions of a given nuclear device or the mass of any of the device components. It simply processes the information supplied by the user to estimate the residual radiation source terms, as well as the radionuclide output and various other details that I'll get into. We've conducted a parametric study using a variety of possible NEDs that could conceivably be used, spanning fission-only to thermonuclear devices with yields ranging from 2 kilotons to 1.2 megatons. We simulate detonation of these devices inside a variety of asteroid material models by modeling the weapon casing as the asteroid material. For each case, we use LWAC to employ a Bateman approximation of neutron propagation to simulate the induced radioactivity of the bolide material, calculating the radioisotope generation and radiological activity. The figure on the right shows the activity in Curies of the irradiated asteroid material, modeled again as the weapon casing, following detonation of a 150 kiloton yield. We use 9 different asteroid material models, 6 of which span various asteroid types, compared with concrete, granite, and soil. The time spans from 0 hours to 10 to the 6 hours following detonation. And the bottom figure shows the residual radiation source terms for each of the relevant components, which are the asteroid material, or the casing, fission products, actinides, and tritium for 2 of the 9 asteroid models. We also look at the potential effect on human life using what's called the composite whole body dose conversion factor, which is unfortunately quite a mouthful. We haven't yet come up with a good way to shorten that. But this calculates the REMS per hour per Curie per square meter, assuming an instantaneous external fallout of irradiated asteroid material and residuals from the NED. Now, of course, we don't expect to find ourselves in a short warning scenario, which necessitates nuclear mitigation, nor would we want to do that if we can help it. But even in worst case scenarios where the entire fragmented bolide intercepts Earth's atmosphere, yielding the burnup of these irradiated fragments, we find that the radiological effects are generally minimal, generally falling below typical terrestrial background levels. Both of these figures show the output of 6 different LWAC runs with varying yields, initial fissile masses, neutron spectra, and weapon types, where the 2 kiloton, 5 kiloton, and 20 kiloton yields are fission only, and the 150, 400 kiloton, and 1200 kiloton runs are thermonuclear weapons. Each of the runs here in these plots uses the C-type asteroid model as the weapon casing. And the left figure shows the activity, again, in Curies, while the right shows that composite whole body dose conversion factor in REMS per hour per Curie per square meter. So to kind of wrap up all that we've been discussing, we've also begun a mission design effort in which we're looking into feasible objects for an actual disruption test. For now, we've narrowed our focus on objects within the 30 to 140 meter diameter class, limiting our current scope to objects which Sasha touched on earlier, which could be reasonably disrupted with a single launcher, that single launcher solution that we're interested in. We additionally focus on objects that have a close approach distance within about 30 lunar distances within the next 10 years or so. And we narrow our query further to minimize the see-through required at departure and maximize that delta V in hopes of impacting the target at high velocity. Though recently, due to some questions posed at an interagency meeting, we've been tasked with investigating impacts at lower velocities on the scale of 5 to 10 kilometers per second, as Sasha was kind of showing earlier with some of those impact sims. So as we get results from those simulations and some others down the line, we're also planning on potentially modeling some missions at these lower speeds in the event that something on that scale may be more feasible. So if anybody in this room or online is interested in or experienced in mission design, please come talk to us. We would love to hear from you and get any help that you may be willing to provide. So to wrap this all up, PI represents an effective multimodal method for planetary defense that could prove useful in a wide range of threat scenarios, spanning both asteroid size and warning time. It represents the first planetary defense strategy that is capable for use against short-range threats, and that's capable for use in that multi-use method. It allows for a logical roadmap toward a robust planetary defense system, creating a single launcher solution for objects within that specific class with at-the-ready capability. And here I have linked our website on the right, as well as two of our recently published papers in the Astrophysical Journal and Acta Astronautica. And we'd be happy to take any questions that anybody might have.
Right. So there is a question online from Alexandra. You just want to unmute and ask your question?
Sure, thanks. So first of all, this is a really great project. I was very excited to hear it. So I have two questions. One is, have you actually tested how the distribution of fragments that arise from this technique, how it depends on the resolution of the simulation? I'll just ask a second one after this, not to confuse you.
Yeah, absolutely. Most of the time, the fragment distribution is mostly impacted by the boulder distribution. Now, the mesh resolution that we use is generally much smaller than the boulder distribution is. So usually the mesh resolution doesn't very much impact the boulder size, the boulder distribution, other than not resolving boulders below the mesh size. Does that answer your question?
Yeah, thanks for that. And to the point that you raised, the second one is related to the initial condition of how the asteroid was actually built. So yeah, my feeling was as well that fragment, this size frequency distribution might be affected by that. So do you have any feeling of what type of an impactor structure would actually produce at least one fragment that could be considered as hazardous to Earth? And if not, then are you planning on testing different structures?
Yeah, absolutely. Most of the results that we found, we've seen that the fragment distribution that we produce has sizes that are much smaller than the initial boulder distribution was. And so we can be fairly confident that the size distribution will be much smaller than the initial boulder distribution is. And this is pretty much the case in all of our simulations where the impact speed is it's where we're impacting faster than the sound speed. We do a pretty good job of pulverizing the material below the size scale of the boulders.
Right, but what if the initial structure and the boulders that make the rubble pile are much bigger than what you have assumed?
Yeah.
Yeah.
So we've done simulations where we have boulders which are roughly the radius of the larger object, and even in those cases, those boulders come apart on a size scale that's almost down to the mesh resolution already is. So it's usually a lot smaller than the original boulder distribution is. And we've even done impacts into homogeneous targets where you don't have a boulder distribution. Those also would come apart in similar ways.
Thanks.
To kind of add to that as well, we didn't talk too much about it here, but we also have a few different modes in which this method works. So for larger objects, particularly that are further away in both space and time, we've also looked at kind of using pi in an enhanced deflection mode. So I don't know if you want to go into that in greater detail, but kind of smacking a very large asteroid to induce a really large momentum transfer through ejecta of material, which could result in still having a large portion of the asteroid left, either in one large piece or several smaller pieces. And in a scenario like that would be, as I said, very, very far away in both space and time, though we are looking into simulating that further to see what that might look like and what those residuals could be.
Thanks.
Question in the back, Robbie? Robert.
Yeah. For this single impactor, you had velocities that were very high, like 20 kilometers per second. So, and that seems like it'd be very hard to achieve with launching from Earth. So have you investigated the actual feasibility or cost of obtaining such high impactor velocity?
Yeah, absolutely. The main point is that we don't actually propose to accelerate our projectile to that speed. Most of the time, especially in the terminal mode, the asteroid is coming into the Earth at that speed already. So you just need to get in front of the asteroid with your projectile effectively. And then the reference frame of the object, you're hitting it at 20 kilometers per second, roughly. Now, of course, that's only the case for a terminal impact where it's about to hit and you're getting the addition of its initial velocity plus the gravitational acceleration from coming close to the Earth where it accelerates up to that speed. There are many cases where, like you're describing, you will not be impacting it at those speeds. And that's why we did a study at 5 and 10 kilometers per second and also supplementing passive impacts with explosives. Yeah.
Bill?
So I find this work really fascinating because it reminds me of stuff that Eric Asfog did long ago on some of this. So I have a question on what's precisely happening in your simulations because I'm curious about it. So when you have your penetrator come in, I can imagine a lot of energy is going to disrupting individual targets, but energy has at least from Eric's simulations, energy often has a trouble going from, let's say, boulder boundary to boulder boundary, gets frustrated. So how much energy is actually just going and taking intact boulders and pushing them out versus breaking them up?
Yeah, it's a very good question. It's actually an area that we're very interested in researching, particularly cases where you don't have a binder material to kind of allow the shock to couple from boulder to boulder to boulder. And it is very likely the case that when you don't, we haven't done that work yet, but it is very likely the case like you're describing where when you don't have a continuous medium to support the shock, that you will just have sort of billiard balls rather than, the shock propagating and doing damage from boulder to boulder. However, the acceleration of those boulders, local to the impact site, you'll have pulverization and those boulders will come apart and their, dispersal velocity will be will be faster than the sound speed in the object as well. And so the sort of billiard balls will be pulverizing each other as it goes along. Now, again, I can't quite answer your question because we haven't run those simulations yet, but it is certainly an area that we're interested in investigating. Yeah.
Are you coming to lunch?
I just had a question.
Well, I was thinking we could do it on the way to lunch.
Yeah, that's fine.
All right. Thank you for the morning session. We are 5 minutes into the lunch, which is why I cut that off. And so far we have 61 people who have been here in person or online. So thank you for that. We will reconvene at the top of the next hour in about 1 hour and 40 minutes. I'm going to leave a break slide up on the Zoom. This room will be behind locked doors, so you should be able to leave your stuff here. And anyone who's interested can walk on down to the Rio. Any of the story people know where we're going, so just follow them if I'm not in the lead. The reservation is under my name, Stuart, although it's probably the only reservation there for 24 people.
They did confirm that there is a reservation.
Okay.
And don't